All right, so this is the final do now for this week, and we're going to go ahead and go over it. So let's start with number 1. In this fiber, copper impurities can lead to an attenuation of roughly 95 decibels, and we know we're looking at copper, per kilometer at wavelengths near 1.6 microns. Such impurities, if graphed as shown, would produce an attenuation response similar to that of. There are a lot of words here that we don't need to know, but we should probably pay attention to the numbers. So we're going to look for something on this graph that has a wavelength similar to 1.6 microns, and an attenuation would be similar to what? So if we take this graph and we go to about 1.6, that's going to lead us to nickel. So it would have an attenuation similar to that of nickel. And our answer is A. Number 2, according to the graph, in a fiber without any impurities, as wavelength increases, power loss will. So if we go back to the graph again, because it says according to the graph, we want no impurities. So what will it do? So that means instead of going down here, we'll just graph it like this. So here, the graph is increasing and then decreasing. So let's see if any of our answers here. The graph, so increases and then decreases, which is why G would be the distractor here, but that's not the answer, because the graph does attenuation. And attenuation is the opposite of power loss. So if attenuation is increasing and then decreasing, then power loss would actually decrease and then increase, which you get from looking at the graph and then also looking at what this means. Because power loss increases as you go down the y-axis. This means that power loss is actually increasing and then decreasing. So if you needed to know where this was, you would get it from the passage here. All right. You can also look here to see the axes, because this is what the number is. So this is where it's important, because if this were a 0 and this were 120, then you would just say increase then decrease. But because this is 0 and this is 120, so you have to make sure that you're really, really paying attention to your axes and how they're labeled here. All right, number 3. If a researcher using a 6.6 micron laser wished to limit power loss, this fluoride glass fiber would be. So fluoride glass fiber, which is what we were looking at. And it wants to eliminate any attenuation. So you don't want any power loss at 6.6. So 6.6, there's a huge amount of power loss here because of the hydroxyl interference. So we probably cannot use that. Let's find an answer choice that agrees. Ideal because attenuation is a minimum. That's the exact opposite of what's happening. That's actually the biggest power loss. Impossible. Nope. We know that's not true because we can see it on the graph. Inefficient because of interference from hydroxyl groups at this wavelength is our answer, because we can see that hydroxyl is interfering in the graph here. Number 4. Suppose a scientist were able to develop a fluoride glass fiber without any hydroxyl impurities. Which of the following predictions would most likely be true? So that means we would take the graph out. So we would still have our impurities like this, but then instead of having the hydroxyl, it would just be the slow decrease. That would be our graph. And remember, this is power loss. This is the biggest power loss. This is the least. Least, largest. Okay. So there will be less power loss in the range between 6 and 7 microns. We know that's where hydroxyl interferes, so that would be yes. The attenuation due to iron impurities would increase. We'll check that. And then the fiber's overall power loss would decrease. If we're not having such huge interference, that's going to be a given. So if we look at these answers, now let's figure out attenuation due to iron. Is iron going to be affected by hydroxyl at all? No, these graphs don't meet or intersect at any point here, so we know it's not going to be number 2 if we look at the graph. So that leaves us only with 1 and 3. Our answer is G. And our last one, number 5. A certain computer communication system requires a cable 5 kilometers long. Based on the data in the graph, what is the minimum power loss that can be achieved using a fluoride glass fiber? So, we want 5 kilometers long. Now let's go back to the passage. The lowest attenuation that could happen for a fluoride glass fiber is here. The lowest power loss is with iron, so that's about 80 in the range of an interference. But then if we actually look at where the lowest power loss is at all, we get it around here. So if we go down here, that is about 5 microns, and then that's 40 decibels per kilometer. But we want this to be 5 kilometers long. So that means that we have to multiply this by 5, because that shows us per 1 kilometer, and 40 times 5 is about 200, which means that D is our answer.